all that matters in physics? First and foremost, physics is a science. Physics is the more apparent and distinctive of the two material sciences, physics and chemistry. Properties of matter, impacts of force, visible motion, dynamics of energy, light, sound, etc. are very common experiences. Chemistry is less apparent, but combustion, fermentation, spoilage of food, medicines, vaccines, home hygiene products, fertilizers, etc. are common. Living things are immensely diverse and active chemical factories and repositories, but we cannot see all this chemistry. Physics is also interesting for being the most mathematized knowledge. It offers mathematically denominated description of the reality. Physics is also interesting for being the most mathematized knowledge. It offers mathematically denominated description of the reality. It is, in fact, entirely mathematized. So much so that physics has propelled a few mathematical foundations and tools. For instance, calculus, delta distribution. Pertinently, chemistry is very closely intertwined with physics, and physics-centered force, motion, matter, and energy quite explain the chemical behavior of matter. It is not much of an exaggeration that theoretical chemistry is a lot of physics. For instance, we study atoms in physics as well as chemistry, and the physical view of atoms, the play of the forces, is critical to explaining the chemical behavior of atoms. Physics is of great importance also because it is the science of structures. Biological cells to plants and animals to airplanes and spaceships and telescope and everything else stays and works as intended because its physical structure supports. Physics is the science of experimental infrastructure and techniques. Thus, the chemical factories, biochemistry creation setups, or geological exploits are just samples of how physics is so pervasive across all sciences. Indeed, of the two material sciences, physics and chemistry, physics may be the one to more explicitly and expansively introduce science. For instance, in chemistry we use concepts such as resonating structures that are not as real, but help us explain the real behavior of matter. Physics and chemistry must first support the understanding of the nature and rationale of science per se. Appreciation of what is scientific knowledge and how it is organically tied to the world of technology, engineering, research, and mathematics too. Expectedly, there is some exploration of science before we come to physics. It may be added that chemistry lessons also starts with science, but bring out somewhat different aspects of science as compared to how it is addressed here. What is science? Science is the knowledge about how we exist and coexist with the world of plants and animals. It is also about all physical parts of the Earth, the solar system, the Milky Way, and beyond. To top it all, science is also how we use this knowledge to thrive, live better, and have more confidence and certainty in our lives. Science is the body of knowledge that explores, encapsulates, expands, and envisages our natural world. Science helps us discover our universe, the living things, the non-living things, and their interactions, biologically, physically, and chemically. Science is the discovered realization of what exists, how it changes, and what is sustainably, repetitively viable. The erudition that we call science is already there. It is how everything in the universe is organized, maintained, and governed. At any point in time, we know only a part of it and keep discovering more about it. Science is how our nature continues to live on, of which we are an integral part, the DNA of the scientific knowledge. One of science's most notable characteristics is that it is a system of systems, a whole. Made of innumerable parts, and the parts interact to create numerous subsystems with the systems. Reiterating, the subsystems are explainable in terms of their parts and the interactions of the parts with one another. The behavior of the subsystems is predictable as it follows a fixed, logically interwoven, and feedback-enabled design. Even then, it is another matter that we are still to find out uncountable systems, subsystems, and parts in nature, let alone explain them. Indeed, as our subconscious mind is aware of, there are definite patterns in the way the system and subsystems behave in nature. Science discovers these patterns in nature. Another word for pattern is order. These patterns keep repeating over and over again in the cycles of time. Any change in the behavior of the subsystems follows the change in the nature of the parts of the subsystems. At one level, the logic of the way the parts interact are rooted in a large set of principles that govern everything. Understanding the pattern is how we can see science as a scripted body of eternal truth, governing laws as deciphered from our understanding of nature. The same laws and knowledge are exercised in cultivating, compensating, and creating a world beyond nature, the man-made world. For instance, the property of water, called surface tension, enables insects to walk on its surface and empowers pharmacists to coat medicinal tablets to improve their odor and taste. A car that is in motion follows the same governing laws as that of the moving planets. And we continue to advance and strengthen the ever-evolving man-made world by untangling the knowledge withheld in nature. For new technologies, we may need new science, new knowledge about how nature works in a similar situation. Technology always lags the knowledge of science. Why science education is a non-negotiable necessity. To better the self-created world and address emerging implacable challenges, we need to apply the knowledge of science. This applied science technology is much beyond computers, gadgets, or spacecraft we often confuse technology with. Anything that is not found naturally and augments our hold on the natural world is technology. Back when the fire was discovered, it was only natural, but inventing the means to start fire by a matchstick is technology. Making paper and cloth from wood or even from waste is technology. Science and technology act in tandem. For instance, science helps us determine the causes and effects of climate change, and technology creates means to address it: green cement, hydrogen ships, or electric planes. Science dictates that there are 4 forces operating on a flying object: thrust, gravity, drag, and lift. And it also educates us that these 4 forces need to be in balance for the object to fly long and fast. And the relevant technology helps us reduce drag by creating streamlined bodies of flying objects. And so, in these unprecedented high-tech times, it is necessary to ensure that the footing of scientific knowledge is broadened to create and support a culture of mass innovation. The state of science education. There is something very extraordinary and interesting about science education in schools. Remarkably, biology is of little meaning to many children even before its formal introduction in grade 6, and it only gets worse with each higher grade. Abnormally, their families see biology as only relevant to those seeking a medical education, and medical education is considered to be too tedious, costly, and financially late blossoming. It is a reflection of their own biology education. Biology education is reduced to rote for exam's sake and drained of all practical, critical benefits of learning biology. Chemistry education is no better, reduced to irreverence in its own unique way. To the point, chemistry is quite seen as opening doors for only specialized and limited kinds of careers. It is also perceived to be a back-end science and technology, hidden from the limelight and specific social recognition. Chemistry textbooks and teaching also slot it as unitary, slicing off its massively interdisciplinary nature, its foundational significance in innovation and evolution. Recall, metallurgy was the first recognized science by humanity. Chemistry loses its soul and essence in the school education system. It may be all apparent that science education is in crisis, and it is because, lo and behold, physics education has its peerless story of oversimplification. From school years till the secondary, physics is mostly considered to be the coolest, easiest science, the science in control, all too obvious, experiential, and universal. However, it all shatters in the post-secondary grades. Physics becomes far too complex, conceptual, and almost mathematics. While force and motion remain the fundamentals of physics, its poor conceptual and nuanced exploration is rarely realized in education at school. The beauty and the preeminence of physics are conspicuous by their absence. Misconceptions on how to improve science education. One popular notion of teaching science is the effectiveness of learning by doing. Albeit it is true that learning by doing is one of the 4 ways to learn new things, the complementing role of the other 3, that is, read, see, converse, is critically important. This fact was substantively indicated in an educational experiment called the Hoshangabad Science Teaching Program, HSTP. HSTP was conducted across grade 6 to 8 of the government schools in India's Hoshangabad district of Madhya Pradesh. It introduced the learning by discovery approach to science education in village schools in place of the textbook-centric learning by rote approach. It was truly among the more ambitious and rigorous educational initiative in India and around the world too. An eminent group of scientists, engineers, educationists, and social activists had formulated a vision of developing a model of school science teaching. It brought to the fore the unique strengths and weaknesses of learning by doing, spanning extensive 30 years between 1972 to 2002. It was a multilateral experiment with the best of credentials in terms of the organizations participating. Students were given a special set of books and had simple yet extensive experimental aids at their disposal. Grade 10th board exam results were used as a proxy for measuring the students' learning gains. However, even after years of experiments, the performance of the students in the Hoshangabad district, specifically in science, was not among the top 10 districts of the state. It was in fact lower than its neighboring districts too. A study of a sample of 25 typical science lessons involving significant practical work found that the teacher's focus in these lessons was predominantly on developing the substantive scientific information of students rather than developing their understanding of scientific inquiry procedures. Practical work was generally effective in getting students to do the intended work with physical objects, but much less effective in getting them to use the intended scientific ideas to guide their actions and reflect upon the data they collected. Learning by doing is indeed ineffective without the larger conceptual frameworks, conversations, and reading. Broadly, activity-based learning often ends up being hands-on, minds-off, and a way to ignore extensive reading and conversations around the activities before and after the activities. Curated. Experiments eclipsed observations and experiences of nature and technologies outside of classrooms. This also left little to discuss about internalized and personalized learning. The language intensity of learning science was poor. Unsurprisingly, another study found that the literacy growth rate in 2001, after nearly 3 decades of HSTP, of the districts bordering Hoshangabad was well over 20%. In contrast, the growth rate in Hoshangabad was under 20%. Learning by doing did not prove to be best way to teach science. The most interesting thing about physics education. Physics education is quite removed from the possibilities of physics also being an entirely theoretical subject. However, this belief does not firmly hold its ground. It may suffice to share that among the most eminent physicists of all time, the lion's share goes to theoretical physicists and not experimental physicists. One would think it to be the other way around in a subject that explains observations, experiences, and experiments. Archimedes, who lived between 287 to 212 BCE, Galileo Galilei, who lived between 1564 to 1642, Isaac Newton, who lived between 1642 to 1727, Michael Faraday, who lived between 1791 to 1867, Albert Einstein, who lived between 1879 to 1955, and Richard Feynman, who lived between 1918 to 1988, were all essentially theoretical physicists. Richard Feynman is noted to have coined the phrase thought experiments to explain how he experimented as a theoretical physicist. The story of theoretical chemistry and chemists is quite similar. Thought experiments and mathematics work in chemistry too. It may be interesting to know that the 2013 Nobel Prize in Chemistry was awarded to 3 theoretical chemists, Martin Karplus, Michael Levitt, and Aria Warshel. Pertinently, physics as well as chemistry are the first-hand witness of the irradiating light of mathematics. For example, Isaac Newton developed calculus to explain the continuously changing motion. Einstein derived relativity theories mathematically. He was an armchair physicist. The interface of science and mathematics can be captured in knowing that science is about logical reasoning based on observations, experiences, and experiments. And mathematics is about logical reasoning. Mathematics is not derived out of anything real, though it is a very real domain of knowledge. It is the language of physics. Every human mind is capable of seeing the universe, and physics equips us with enough to visualize and conceptualize the sustaining dynamics of all that is there in the universe using logical reasoning. Physics education. The imperative from the aforementioned aspects of widely practiced physics education and theoretical physics is loud and clear. We need a judicious mix of learning by doing and envisioning and articulating physical processes. It is also writ large that the balance must tilt in the favor of hypothesizing out of observations and experiences. To be true, theoretical underpinnings are essential even to conceptualize, set up, trigger, and sustain experiments and interpret the outcomes. At its core, experiments are the means to observe and experience physical phenomena that are beyond the personal realm. Physics education in schools is mostly devoid of debates, discussions, and deliberate readings. Teachers usually deliver substantive scientific laws and facts, and often fail to help learners connect the dots of everyday experiences using the laws. Unfortunately, teachers themselves often fail to register and logicalize their lived experiences consciously. Curricular physics books should enable learners to weave together their own visualizations and interpretations of everyday living in a logical framework. The books should enable learners to harness the relevant physical laws in explaining and predicting the physical behavior of things and their interactions. The books should be richly narrated, thinking physically. The fast consolidating knowledge society has already changed what is valuable knowledge, the critical and creative thinking ability. No facet of knowledge is inaccessible or unique in a context per se. In the times ahead, the purpose of exploring any knowledge domain is to hone and refine the pace and effectiveness of thinking in the constructs of the domain. Curricular books should contemporize learning. They need to pivot on fine-tuning the conceptual depth and breeding intellectual discourse, thereby providing a safe space to visualize and conversate. Thank you.